Hello my schoolers, you are welcome to my school YouTube channel and my name is Frank. In today's video we shall be learning about vibration in strings and pipes, which is a continuation of our physics topic by topic video lessons. So get your pens and paper ready, relax, do not go anywhere, and I'll be right back. You are welcome back to my school YouTube channel. Like I said earlier on, today we shall be learning about vibration in strings and pipes. Now take note that this topic is still underway based on how we classify the topics. Okay, so before we dive into the topic proper, let us quickly go through the objective for today's lesson. So at the end of this lesson, scholars should be able to explain the formation of standing waves and produce these waves in stretching strings. B. Use resonance tube to determine the velocity of sound in air. C. Classify musical instruments into I. Wind, II. Stringed, and III. Percussion instruments. And D. Explain the physical principles involved in use of wind, string, and percussion instruments. So let's move to the next slide to begin with our lesson. So we will kick off with vibration in strings, right? So the diagram below shows a string that is fixed at both ends, okay? So when a stretched string fixed at both ends is gently plucked at the middle, a transverse stationary wave is set up in the string. Okay, so let's quickly explain the meaning of transverse stationary wave. So those are two words that actually join together. So when we say transverse wave, we're actually saying that the displacement of the particle is perpendicular to the direction of propagation of the wave. And when we say stationary, okay, we are referring to two waves. Okay, we are referring to a combination of two waves with the same amplitude and frequency but moving in opposite direction. Okay, so from the diagram you can see that the length of the string is equals to 1 lambda divided by 2. Okay, remember from the diagram of wave, okay, so let me just make a little sketch here. So of course the reason why I'm doing this is that I'm trying to show you why just a loop, okay, is equals to 1 lambda divided by 2. Okay, so this is our wave motion, right? And remember that the distance between two successive crests, okay, is equals to 1 wavelength, right? And remember that wavelength is usually represented with lambda, right? Now if you look at this line, you actually divided this loop into 2. And if you look at this other line, you actually divided it into 2. So if we join these two loops together, we'll be having 1 full loops, right? So meaning that 2 full loops, which is here, the upper ones, which is these two halves joined together to form 1, and this one is equals to 1 lambda, right? Now, but if you check this diagram, we only have 1 loop. So in that case, that 1 loop will be equals to 1 wavelength divided by 2, okay? And that is also equal to the length of the string, okay? So the simplest mode of vibration of the wire is what is shown above, right? Which is just a single loop. And remember that the distance between the fixed ends equal half a wavelength. Of course, this is very important for us to take note of, because more or less like serve as the basis for everything that we are going to be discussing about today. Okay, so from the diagram, we can see that L, which is the length of the string, is equals to 1 lambda divided by 2. Okay, so let's explain this parameter. So where the L is the distance between the fixed end, okay, and lambda is equals to wavelength, right? So if we decide to make lambda the subject of formula here, by simply cross multiplying, we'll be having lambda to be equals to 2L, right? But remember that frequency is equals to velocity all over lambda, right? From the relationship V is equals to F lambda. So here we decide to make F the subject of formula. Okay, so that's how we arrive this formula. F is equals to velocity all over lambda. But remember that from here, our lambda is equals to 2L, right? So in place of lambda in this formula, we replace it with 2L, okay? So that F is now equals to velocity all over to L, right? And this is the simplest mode of vibration. Okay, so the frequency in this case is now referred to as fundamental frequency. So let's move to the next slide. So that frequency, okay, is called fundamental frequency F0, right? And the vibration is called fundamental mode of vibration. Okay, now this frequency, which is called fundamental frequency, or it can as well be referred to as the first harmonics. Okay, so we are going to define these terms: fundamental frequency and first harmonic. So just know that fundamental frequency and first harmonic are the same in terms of formula. Okay, so the fundamental frequency F0 is the lowest frequency obtained from a plucked string. Okay, the lowest frequency obtained from a plucked string is what is referred to as fundamental frequency. Okay, now it is also possible to produce higher frequencies, which are whole number multiples of the fundamental frequency. So the whole number multiples of the fundamental frequency are called harmonics. Okay, the whole number multiples of the fundamental frequency are what is referred to, or are what are called harmonics. So any resonant frequencies above the fundamental frequencies are called overtones. So take note of these three terms: fundamental frequency, harmonics, and overtone. So any resonant frequencies that is above, that is higher than the fundamental frequency, is what is referred to as overtones, right? Now, in order for us to obtain other overtones, okay, to obtain other harmonics or overtones, what we have to do is just to increase the number of loops, right? So in that case, the string will be touched slightly at its center, okay, and at the same time, the string is plucked at a point. Now, a quarter of L from a fixed end, the string vibrates in two loops. So in this case, we now have two loops. Now, remember that for one loop, more or less serve as the basis. So now we have two loops. And the reason why we are having two loops is because we want to obtain other harmonics or overtones, right? So now we now have two loops. So the vibration of the two loops is called first overtone and second harmonics. The vibration of the two loops is called first overtones and second harmonic. So on the other slide, so we are going to also derive a formula here. Now, but take note, the length of the string still remains the same. But what only happened here is that the string was touched in the middle, right, to create two loops instead of one loop. Now, remember that each loop here is equals to 1 lambda divided by 2. So in this case, we have two loops, and those two loops, each of them is 1 lambda divided by 2. So of course, the length now of the string in this case will now be equals to lambda divided by 2 plus lambda divided by 2, because the length of the string is now equals to 2 loops, right? So let's move to the next slide so that you can see what I was trying to explain. So here, L is equals to lambda over 2 for the first loop plus lambda over 2 for the second loop, because we now have two loops. And the answer is because we want to obtain an overtone, okay, or harmonics. Now, if we add these two together, of course, we're going to solve this little fraction. Of course, here the LCM is 2, right? So 2 into 2 is 1. Then 1 times lambda is also equal to lambda. So we have lambda plus, here still the same thing. So at the numerator, we'll be having 2 lambdas divided by 2. So the 2 will cancel 2, so that L is equals to lambda. Okay, in the case of two loops, L is equals to a lambda, right? The frequency in this case is F1, so we'll call it F1 instead of calling it F0, right? Because this is no longer the fundamental frequency. Okay, now F1, but remember that F is equals to, of course, I've already shown you how this formula came about. Okay, so F1 is equals to velocity all over lambda, but here, okay, L is equals to lambda. So in place of lambda, we are going to replace it with L. Okay, so that F1 is equals to V all over L, right? And this F1 is also equals to 2 times the fundamental frequency. Okay, so this we call the second harmonics or the first overtone. Okay, so this we call the second harmonic or first overtone. So for example, if you are asked to calculate for first overtone and you are given the fundamental frequency. So that fundamental frequency that is just given to you, okay, you multiply it by 2 to get the overtone or to get the second harmonics. Okay, so as we progress in this lesson, you will see some examples, okay, in order for you to really understand what is going on here. Okay, so the loop again, that same string can as well be touched again to create 3 loops, right? But remember, each of the loops is equals to lambda divided by 2, lambda divided by 2. But remember, nothing has altered the length of the string. So the length of the string still remains the same, which is L. But in this case now, that L is now equals to lambda divided by 2 plus lambda divided by 2 plus lambda divided by 2, because we now have 3 loops. We have made 3 loops from the length of the string, right? So here L is equals to lambda divided by 2 plus lambda divided by 2 plus lambda divided by 2. Of course, the SCM here is 2. Then in this case, since the denominators are the same, right, we simply add the numerators. So lambda plus lambda plus lambda, that will be equals to 3 lambda all over 2. Okay, so that L is equals to 3 lambda or 3 lambdas all over 2, right? Now here we will have to make lambda the subject of formula. So if we make lambda the subject of formula by simply cross multiplying, so we'll be having 2L to be equals to 3 lambda. But since we want to make lambda the subject of formula, we simply divide both sides by 3. Okay, so that lambda now is now equals to 2L all over 3. Okay, so in this case, the frequency we call F2. But remember that frequency equals to velocity all over lambda. So in place of lambda, we will replace it with 2L all over 3. So lambda here is replaced with 2L all over 3. Of course, this 3 is going to go up, right? So once this 3 go up, we'll be having F2 to be equals to 3V all over 2L. Okay, so that F2 is equals to 3V all over 2L, right? And this is also equals to 3F0. But remember that our F0 here is the fundamental frequency, okay, which is the simplest mode of vibration of a string. Okay, so take note of that. So this amounts to the third harmonics or second over 2. So it's very easy to remember. So this is it. When we have 3 loops, that is when we will have the third harmonics or second over 2. When we have 2 loops, then we will have second harmonics or first over 2. Then when we have just a single loop, that is when we will obtain the fundamental frequency. So it's very, very easy to understand. So let's move to the next slide to continue with our lesson. Okay, so we can continue to increase the number of loops in order for us to obtain the fourth or the third over 2, right? So if we decide to use a vibration of 4 loops, there we'll be having L to be equals to lambda all over 2 plus lambda all over 2 plus lambda all over 2 plus lambda all over 2. Of course, the denominator of these fractions is 2, right? So we simply add the numerator. So in this case, that will be equals to 4 because we have 1, 2, 3, 4 lambdas, right? So you'll be having 4 lambda all over 2. So 2 here is 1, 2 into this 4 is 2. So that at the end of the day, our L is equals to 2 lambda when we have a vibration of 4 loops, right? So here we just make lambda the subject of formula by simply dividing both sides by 2. So that lambda now becomes, in this case, now becomes L all over 2. So the frequency in this case, when the number of loops is equals to 4, we call F3, right? But remember that frequency is velocity all over lambda. So in place of lambda, we replace it with L all over 2. Okay, so here we'll be having L all over 2 in place of this lambda. Of course, these 2 will move up so that we'll now be having the F3 to be equals to 2V all over L. And this is also equals to 4 fundamental frequency, which is 4F0. And this we call the first harmonics or third overtone. Of course, we can continue to increase the number of loops, okay, in order for us to obtain the fifth harmonics or the fourth overtone. If you want to obtain the fifth harmonic, it's just for you to increase the vibration of loops to 5. Okay, so that will give us the fifth harmonics or the fourth overtone. So we just follow the same step. So if we want to obtain the sixth harmonic, we just increase the number of loops to 6, right? So and so on, right? Now it should be noted here that the fundamental frequency is the lowest frequency, but the strongest audible frequency. Okay, while the overtones are higher frequencies, but quieter than the fundamental frequency, meaning that they are not as loud or as audible as the fundamental frequency or fundamental note. Okay, so let's move to the next slide. So on the next slide here, we want to discuss about an instrument used to study the frequency of notes obtained from string instrument. And that instrument or that device is called the sonometer. Okay, so a sonometer is an instrument used to study the frequency of notes obtained from string instruments. So the diagram below is the diagram of a sonometer. So the sonometer consists of a hollow sounding box, which is this, okay, along whose length is a string stretched. The string is attached to a peg at one end, and the free end is passed over a groove pulley, which is this, okay, a grooved smooth pulley. To the free end is an attached weight, which is this, by which the string is stretched out. So the stretched out just simply means tight, okay, something that's not loose. Okay, that's what this word means. Okay, so the two movable knife edges function as fixed end and as well used to vary the length of the string between the fixed ends. So let's move to the next slide. Now the weight W equals the tension T in the string. Okay, when the weight in the string is kept constant, the frequency and the length are varied, and the relationship below is obtained. Okay, so when the weight, which is the same thing as the tension in the string, is kept constant, then we'll be having F to be inversely proportional, okay, to the length. Meaning that the shorter the length, the higher the frequency, since the relationship between frequency and length here is that of inverse. Okay, as one increases, the other reduces. Okay, so the shorter the length, the higher the frequency, or if we say the longer the length, then the shorter the frequency. So when the length is kept constant and the frequency and the tension are varied, then we will obtain that F is directly proportional to the square root of tension. So the higher the tension, the higher the frequency. And the reason for that is because the relationship between frequency and tension is direct, meaning that as frequency increases, tension too will increase, or as tension decreases, frequency will decrease. So when both the length of the string and the tension are kept constant, and the strings of different mass per unit length are used with varying frequency, then we will obtain this relationship that F is inversely proportional to 1 over the square root of M. Now remember here that M here stands for mass per unit length. Okay, so the smaller the mass per unit length, that is, it has to do with the thickness of the string. Okay, mass per unit length has to do with the thickness of the string. Okay, the higher the frequency. And the reason for that is because the relationship between frequency and mass per unit length is inverse. Okay, meaning that as frequency increases, mass per unit length decreases. As mass per unit length increases, frequency decreases, vice versa. Okay, so let's move to the next slide. So when the three relationships above, which is those three relationships that we have discussed earlier on, when these three relationships are combined together, then we'll now obtain F is proportional to 1 over L, then times the square root of T all over M, right? Of course, here we need to introduce a constant. So once we introduce a constant, then this proportionality symbol will change, okay, to equal to, right? So here we will obtain an equation, but here is only showing a relationship. Okay, so F is now equals to K all over L, then times the square root of T all over M. So each of these parameters, we are going to define what they are. So F is equals to frequency of vibration of string, while L is equals to length of string, T is equals to tension in the string, and m is equals to mass per unit length of the string, while k is equals to a constant which depends on the number of loops. Okay, so relating this to the fundamental frequency now, so the fundamental frequency in this case will now be equals to 1 over 2L. Okay, 1 over 2L. Now remember, this is it. Now that V from here, from F is equals to V all over lambda, right? Remember here in this case that for our fundamental frequency, F naught is equals to V all over 2L, right? So in this case, this V is actually taken as constant, okay? So that is why in this place we have 1, right? In this place we have 1. Now in place of V, we'll be having that the fundamental frequency is equals to 1 over 2L, then times the square root of T all over M, okay? So F1, which is equals to 2 times fundamental frequency, that is when we have 2 loops, or when the first overtone or second harmonic is obtained, right? So we'll now be having this to be equals to 1 over L, then the square root of T all over M, right? Remember that what happened here is that this F, everything here, okay, we actually replace it with F naught, because F naught is equals to this. So in place of F naught here, we replace it with everything we have here, so that these two we cancel out these two, so that we now obtain this formula, which is 1 over L, then the square times the square root of T all over M. So this gives us the second harmonics or the first overtone. Okay, so for the third one, we can as well still do the same thing. So F3, that is when we have 3 loops, or when we have the third harmonics or second overtone, right? So in place of F naught here, we replace it with the whole of this. So if we replace it, we'll be having 3 over 2L, then times root T all over M, and so on. Okay? Now, it should be noted that the speed of transverse waves along a stretched string is given by V is equals to the square root of T all over M. Okay, so that is actually what happened here. So in place of that V, okay, we actually replace it with root T all over M. Okay, we replace it with T all over M. Okay, so I'm emphasizing on that for a reason, so that we'll take note of that. So if you are asked to calculate for the speed of a transverse wave along a stretched string, you simply make use of this formula. Okay, V is equals to root T all over M. But remember that T here stands for tension and M here stands for mass per unit length of the string. Okay, so let's move to the next slide. So here are some work examples for us to test everything that we'll be saying since. Okay, so let's begin with the first one. The first question: find the frequency of the first 3 harmonics of a piano string of length 1.5 meter if the velocity of the wave on the string is 120 meter per second. So here we are asked to calculate the first 3 harmonics. Now remember that the first harmonic is equal to the fundamental frequency, while the second harmonic is 2 times the fundamental frequency. The third harmonic is 3 times the fundamental frequency. So it's very, very easy. Now remember here, this question is about a string. So let's even assume that you don't know the formula for calculating the fundamental frequency, but you can easily generate it, since you know that the fundamental frequency is obtained when you have only 1 loop. Okay, it is obtained when you have only 1 loop. So with that 1 loop, I will know that that 1 loop is equals to lambda all over 2, right? That 1 loop is equals to lambda all over 2, and that is also equals to the length of the string. So from there, you substitute it into F is equals to V all over lambda, right, to obtain the fundamental frequency, which is exactly what we have here. So to obtain the fundamental frequency, to solve for the first harmonic, which is the fundamental frequency, we make use of this formula. F naught is equals to V all over 2L. Remember, V stands for velocity and L stands for the length of the string. So we just substitute, because in this question, the length of the string is given to us to be equals to 1.5 meters, and the velocity is of the wave is given to us to be equals to 120 meter per second. So we just substitute. So in place of V, we replace it with 120, and in place of L, we replace it with 1.5, right? But remember that 2 times 1.5 is 3. So 120 divided by 3, that will be equals to 40 hertz, right? So that is the fundamental frequency, and which is also equals to the first harmonics. Okay, so to obtain the second harmonic, we simply multiply the fundamental frequency or the first harmonics by 2. So don't be confused. The fundamental frequency is the same as the first harmonics. Okay, that's what I'm trying to emphasize here. The fundamental frequency is the same or is equal to the first harmonic. So to obtain the second harmonic, we simply multiply the fundamental frequency, which is the first harmonic, by 2. So in this case, we're having 2 times 40, and that is equals to 80 hertz for the second harmonic. So for the third, we multiply the fundamental frequency or the first harmonics by 3. Okay, so in this case, we'll be having 3 times 40, that will be equals to 120. Okay, so the first harmonics is equals to 40 hertz, while the second one is equals to 80 hertz, while the third one is equals to 120 hertz. So the first 3 harmonics are 40, 80, and 120 hertz. Okay, so let's move on to example 2. A vibrator of frequency 60 hertz is used in generating transverse stationary waves in a long thin wire. So here they are still talking about a string. If the average distance between successive nodes on the wire is 45 centimeters, find the speed of the transverse waves in the wire. So here basically what they are telling us here is that frequency is equals to 60 hertz. Okay, and then the length of the string is equals to 45 centimeters. So here we are asked to find the speed of the transverse waves in the wire. So remember that V is equals to F times lambda, right? So where V stands for speed. Now remember that speed is equals to frequency times wavelength, right? So V stands for speed, F for frequency, and lambda represent wavelength. Okay, but in the question we are giving F to be equals to 60 hertz and the length of the wire to be equals to 45 meters, right? So since this is in its basic unit, of course this is not in its basic unit, we have to convert it to meter, right? So we simply divide by 100 because 1 meter is equals to 100 centimeters. So to convert these 45 centimeters to meters, we simply divide by 100. So if we divide this 45 by 100, we will obtain 0.45 meters. So let's move to the next slide. Now, remember that here that lambda is equals to 2L. The reason is because we only have, in that question, we only have a single loop. Okay, a single loop, and they said between 2 successive nodes, right? Now, this is for a single loop. So this place here is 1 node and this is another node. Okay, so those are the 2 successive nodes. So lambda is equals to 2L. Remember that L is equals to lambda all over 2, right? So if we decide to make lambda the subject of formula, we'll be having lambda to be equals to 2L. So that is how we obtain this lambda to be equals to 2L. So we multiply the length by 2 since lambda is equals to 2L. So in place of L here, we replace with 0.45, right? So that we'll be having 2 times 0.45, and that will be equals to 0.90 meters. But remember, velocity is equals to frequency times lambda. So we just substitute these values that are given to us. Remember, frequency is given to us equals to 60, and we obtain the wavelength to be equals to 0.90. So we just multiply these 2 values, which is 0.9 for the wavelength, okay, and 60 for the frequency. So if we multiply both of them together, that will be equals to 45 meters per second. Okay, meaning that the wave, the speed of the wave is equals to 45 meters per second. Of course, this is very easy to multiply. Remember that 0.9 is also equals to 9 all over 10. So 9 all over 10 will multiply it by 60. Here, 0 will cancel out 0. So that will now be having 9 times 6. Remember, 9 times 6 is equals to 54. Okay, so that is the answer for the second example. Now for the third example, we are asked that when the tension in a sonometer wire is doubled, the ratio of the new frequency to the initial frequency is, so we are actually asked to find the ratio of the new frequency to the initial frequency. But remember, when we are discussing about sonometer, right, one of the relationships that we obtain based on our discussion, is that frequency is directly proportional to tension. Okay, so that here F is directly proportional to tension. So we can decide to introduce a constant. So if we introduce a constant, of course, what we have here is relationship. We can't work with this. Okay, this is just a relationship showing us that when frequency increases, tension is going to increase. When tension reduces, frequency is going to reduce. So you can actually work with this. This is not an equation, it's just a relationship. So to make it an equation, you will have to introduce a constant. So by the time you introduce a constant, then this symbol automatically changes to equal to. Okay, so that here F is equals to K, then root tension. So here we call F1 as the initial frequency, T1 as the initial tension, F2 as the new frequency, and T2, which is also the new tension in this case, as the case may be, right? But here we are told that the tension in the wire is doubled. So if the tension in the wire initially is T1, okay, then the tension, the new tension now will now be equals to 2 times T1. So that here T2 is equals to 2 times T1. Since the tension in the wire initially, the initial tension was doubled, okay, to obtain the new tension. So that is why T2 is equals to 2 times T1, right? So since F is equals to K root T, of course we make T the Sonometer formula by dividing both sides by root T. So if we divide both sides by root T, we'll be having K to be equals to F all over root T. Of course, it's a constant, meaning that we can have F1, okay, all over the tension to be equals to, okay, let's call it T1, to be equals to F2 all over root T2, right? Now, we can decide to move this tension here. Of course, if we cross multiply, we'll be having F1, then root T2 to be equals to F2, then root T1, right? But remember that in this question, we are asked to calculate for the ratio of the new frequencies, which is F2 all over F1. Of course, we can easily obtain that from here by simply dividing both sides by F1. So if we divide here by F1, right, so we'll be having F2 all over F1, then here we still have our T1. So here we'll be having root T2, right? Now, we will have to multiply both sides by 1 over root T1 so that we can clear this T1 from this side, okay? So if we do that, we'll be having F2 all over F1 to be equals to root T2 all over root T1. So that is how we obtain this formula, okay? That is how we obtain this formula. So I'm just showing you how this formula came about, this particular one, okay? Of course, this one is what we actually have here, okay? So I'm just showing you how this one came about. So we'll be having F2 all over F1 to be equals to root T2 all over root T1. In place of T2, which is from here, in place of T2, we'll replace it with 2 times T1, of course, all over root T1, right? Then this root 2T1, we can actually break it down according to the law of sort, right? So this is also equals to root 2, then times root T1, so that root T1 can cancel out with root T1. So if they cancel out, we'll now be having that the ratio of the new frequency to the initial frequency, which is F2 all over F1 is equals to root 2. So let's move to the next slide to continue with our lesson. So this should be the last example for today, okay, which is example 4. So a sonometer wire of linear density 0.08 kilogram per meter subjected to a tension of 800 Newton is plucked. Calculate the speed of a pulse which moves from one end of the wire to the other. So basically here we are calculating the velocity or the speed of wave in a string, okay? So remember that to calculate that, we simply use the formula V is equals to root T all over M. But remember that M here stands for mass per unit length. So mass per unit length is the same thing as linear density, okay? Mass per unit length. That is mass all over length, okay? So the unit of mass, okay, is kilogram, while the unit of length is meter, which is the same thing as this. So another word for mass per unit length is linear density. So take note of that. So here we just substitute, since we already know M, which is mass per unit length or linear density, to be equals to 0.08 kilogram per meter, and the tension is given to us to be equals to 800 Newton. So we just substitute into this formula. So in place of T, we replace it with 800, while in place of M, we replace it with 0.08, okay? So first of all, we have to remove this decimal point. So to remove this decimal point from the denominator here, we have to multiply it by 100. So if we multiply this by 100, okay, we'll now be having 8. And we also do the same thing to the numerator. Because if we don't do the same thing to the numerator, that means we have altered the fraction. The fraction is no longer correct. So since we multiply the denominator by 100, in order to clear the decimal point, we also do the same thing to the numerator, okay? So if we multiply 0.08 by 100, we'll be having 8. And if we multiply 800 by 100, then in that case, we'll be having 80,000, right? So 8 into 8, that will be 1. So that at the end of the day, we now have root 10,000. And root 10,000 is equals to 100, okay? So that the speed of the pulse is equals to 100 meters per second. So this is where we draw the curtain for the preview of today's video. I hope you enjoy it, okay? But you can enjoy the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will need to subscribe to enjoy the complete video. Now don't forget that in the complete video we actually completed the rest part of the objective for today's lesson, such as vibration in pipes. We also talked about classification of musical instruments. We also talked about the measurement of the speed of sound in air, okay? So those are some of the topics that we discuss in the complete video, and also with calculation, okay, just to emphasize everything that we have been learning. So do not forget to hit the like button, click on the subscribe button, and lastly tap on the notification bell to get informed as soon as we release the next video.